Hey guys, how's it going? Mr. Mitchell here. In this video, I'm going to go over some worked examples covering types of uncertainty. So specifically, we're going to look at how to do scale reading uncertainty, mean and random uncertainty, and systematic uncertainty. If you haven't already done so, check out my video covering the theory on types of uncertainty, as that will help you understand what we're doing here. So let's get started. Let's make a start by looking at scale reading uncertainty. We're going to practice both analog and digital scales. So question 1 says, what is the reading uncertainty in the analog scale shown below? Well, we need to remember that reading uncertainty for an analog scale is equal to plus or minus half of the smallest scale division. So if we look at our example here, we've got 10 little divisions between 6 and 7, so that means each little scale division must be 0.1. So we've got plus or minus half of 0.1 centimetres, which gives us plus or minus 0.05 centimetres. Question 2 has 3 parts, parts A, B and C, and it says for each of the analog scales shown below, write down the reading and estimate the scale reading uncertainty, stating your answers in absolute form. In part A, we've got a scale in millimetres, and you'll see that the arrow points to this division marking here after halfway between 2 and the 4, so that's obviously going to be 3 between the 2 and the 4, and there's 5 little divisions between the 3 and the 4 in that case, which means that the arrow is pointing to the reading of 3.2 millimeters. And remember, to get the scale reading uncertainty in this analog scale, it's plus or minus half of the smallest scale division, which is plus or minus half of the 0.2 between each little division, which gives us plus or minus 0.1 millimeters. And if we want to write that now in absolute form, remember we do that with our brackets, and we have our reading plus or minus our uncertainty, with the units appearing outside of the brackets. So that would look like this. So we have 3.2 plus or minus 0.1 millimeters. Part B is a scale in centimeters, and the arrow is pointing to this third division here. Now we have 10 divisions between the 2 and the 3, so that arrow must be pointing to 2.3 centimeters. Just as before, we've got our scale reading uncertainty is equal to plus or minus half of the smallest scale division, and that means it's plus or minus half of 0.1 centimeters, which gives us plus or minus 0.05 centimeters. Remember, we want to state our answer in absolute form, so to do that it would be 2.3 centimeters plus or minus the 0.05 centimeters, but if we put it in brackets we don't need to say centimeters twice, so it looks like this. 2.3 plus or minus 0.05 centimeters. And the last one for analog scales, part C, we've got this scale in degrees Celsius, and the arrow is pointing to this larger division marking here, which is halfway between the 0.2 and the 0.3, which means that it must be 0.25 degrees Celsius. Same as before, our scale reading uncertainty in this analog scale is equal to plus or minus half of the smallest scale division, which is plus or minus half of the 0.01 degrees Celsius. The reason it's 0.01 is because we'll get 10 division markings between 0.1 and 0.2. So plus or minus a half of 0.01 degrees Celsius gives us plus or minus 0.005 degrees Celsius. And writing that in absolute form then, with the reading plus or minus the uncertainty, we have 0.25 plus or minus 0.005 degrees Celsius. Moving on to digital scales now, question 3 says, what is the reading uncertainty in the digital scale shown below? So it's 8.94 seconds appears on our screen. So remember that the reading uncertainty in a digital scale is equal to plus or minus 1 of the least significant digit. So the least significant digit in this case is the 4, but remember the actual value of the 4 doesn't matter, it's just the least value that this can take, which is a 1, so this is plus or minus 0.01 seconds. Applying this same method to these 3 parts A, B and C to question 4, we have for each of the digital scales shown below, write down the reading and estimate the scale reading uncertainty, stating your answers in absolute form. So for part A, we've got 7.84 seconds, so the reading is quite straightforward, it's just simply 7.84 seconds. And our uncertainty is, remember, plus or minus 1 of the least significant digit, which is going to be, again, the 0.01, so we have equal to plus or minus 0.01 seconds. Writing this in absolute form, we have 7.84 plus or minus 0.01 seconds. Part B is 1.005 amps, so this might be a reading on an ammeter, for example, and the reading is therefore going to be quite straightforward, 1.005 amps, and our uncertainty is, in the digital scale, plus or minus 1 of the least significant digit, and the least significant digit here is going to be the 5, but remember the 5 doesn't matter, it's the smallest non-zero value that this number can take, which is 0.001, so our reading uncertainty is plus or minus 0.001 amps. Writing this in absolute form, we have 1.005 plus or minus 0.001 amps. Part C is 195, but notice we've got milliamps instead of just amps here, so our reading is going to be 195 milliamps. Our reading uncertainty in the digital scale is plus or minus 1 of the least significant digit. The least significant digit would be this number taking a 1 here, so it's just going to be a 1. So it's plus or minus 1 milliamps, and writing this in absolute form, we have 195 plus or minus 1 milliamp. Moving on to mean and random uncertainty now, we're going to look at 3 examples of this. The first few are broken down into parts, and the last one is just one big question. So let's get going with this. Question 1 says, in an experiment to investigate Ohm's law, a Nat5 pupil records values of current every time she changes the voltage. The current readings are as follows. So we've got these 5 values here, and it says calculate the mean current. So it should be quite straightforward. Remember, to calculate a mean, we add them all up and we divide by how many measurements are taken. So we've got the sum of the measurements divided by n, which gives us this divided by 5, which is equal to 0.44 amps. And notice that I've put that in 2 decimal places as well, because all of my results were in 2 decimal places. Part B then says calculate the random uncertainty in the mean. So remember, to do this, we've got the random uncertainty is equal to the maximum value minus the minimum value divided by the number of measurements. So our biggest value here is the 0.45. Take away the smallest value there, which is 0.42, divided by 5. This gives us plus or minus 0.006 amps. And remember, we want to state our random uncertainties to 1 or 2 significant figures. In this case, we've got 1 significant figure at the 6. Question 2 says a misbehaving student is forced to time 10 swings of a pendulum as a punishment. They repeat this 5 times. The readings obtained are these here. And it says calculate the mean time for the 10 swings. Now notice that the 10 is just kind of trying to throw you off. We don't actually need to do anything with the number 10. It's just telling us that there were 10 swings, but there's 5 results in total here. So our mean is equal to the sum of the measurements over n. We add them all up and we divide by 5 and we get 1.2 seconds. Part B says to calculate the random uncertainty in the mean and then state your final answer in absolute form. So we need to state it in the form of mean plus or minus uncertainty. So we use our relationship for random uncertainty, which is equal to maximum value minus minimum value over n. So our biggest value is the 1.4, and we take away our smallest value, the 1.1, and we divide by 5. And this gives us an answer of plus or minus 0.06 seconds. Stating this in absolute form, we have 1.2 plus or minus 0.06 seconds. And again, our random uncertainty is stated to 1 significant figure. The last example for mean and random uncertainty says that a student uses light gates and a data logger to measure the acceleration of a trolley as it moves down a slope. The following results were obtained. So we've got these acceleration values in meters per second, and these are the measurements here. So calculate the mean acceleration and the corresponding random uncertainty. State your final answer in absolute form. So just like what we did in question 2, but this time it's not breaking it down into parts for us. So the mean is given by the sum of the measurements over n. So we add them all up and divide by 8. In this case, we've got 8 measurements, and this gives us an answer of 5.19 meters per second squared. The random uncertainty in this is then given by random uncertainty equals maximum value minus minimum value over n, which gives us 5.24 minus 5.12 divided by 8, and this gives us an answer of plus or minus 0.015 meters per second squared. Now this is 2 significant figures, but that's okay. And stating this in absolute form, we have 5.19 plus or minus 0.015 meters per second squared. The last couple of examples to look at are for systematic uncertainty. So question 1 says simply explain what is meant by a systematic uncertainty. Well, remember that a systematic uncertainty occurs when all measurements taken are affected in the same way. So this is straight from the theory, straight from the notes. For example, the readings may be all too high or all too low due to a faulty measuring device or failure to calibrate a device to 0 before taking measurements. And remember, we can see systematic uncertainties on graphs because they might be offset from the origin. So in question 2, this is what this question is concerned about. In an experiment to investigate Ohm's law, a student obtains the following graph of voltage against current. So you should expect to get a straight line through the origin. So we've got voltage on the y-axis and current on the x-axis, and it says to redraw the above graph and add another line to show what the line of best fit would look like if there was a systematic uncertainty in the current readings, i.e. they were all too high. Well, remember, if we had voltage readings that were all too high, then the line would start up here. But in this case, we've got current readings that are all too high, so it's going to look like this instead. That's all from me, guys. I hope you found the video useful. If you did, give it a thumbs up, subscribe, and I'll see you in the next one. Take care.